Okay, I've started the recording, and we are talking about perfect and imperfect information in dynamic games. And we started from discussing perfect information. Game with perfect information is a game when all players are aware about what other players did at the previous step, basically who and how moved before them. And the example of this is the game we've discussed a week ago with 3 women who need to decide whether to contribute to a street garden or not. So Emily is the first to make her decision, then Nina makes her decision based on or using the information about how Emily behaved before Nina, and then Talia makes her decision using the information about how Nina and Emily behaved before her. So game with imperfect information is a new idea for us. And in a game of imperfect information, player cannot distinguish between nodes. So this is how we show it on the tree. So in this particular, it's called information sets. We'll introduce this term, I think, in the next slide. In this particular information set, this player cannot distinguish, cannot distinguish between 2 nodes. So actually what happens in this game? There is a king who decides what taxes to put, high taxes or low. There are people like king servants who decide whether to steal or not steal from the king and from the peasants. So P are peasants. So peasants pay their money to king services, and they can keep some parts of money, or they can give everything to king. So they can steal or not steal. And it's peasants, they don't know whether they steal or not steal. So they don't know where they actually, here or here, right? And they have to decide whether to rebel or not without information where they are in this node or in this nodes. So this is called asymmetric information, because M is aware where P is now. M is aware whether they steal or not, but P they don't have this information. Peasants don't have this information. In games with incomplete information, so it's imperfect here and incomplete here, we have a nature. So nature is not strategic player. So nature doesn't care about outcomes. There are no outcomes associated with nature. So nature just distributes chances. So let's say we play a game with my wife where to go on the Sundays morning, and I have my priorities and my wife has her priorities. But there is also nature in a very direct sense, weather influence our payoffs. For example, if I want to go to the park, then if weather is fine, we can enjoy it a lot. But if weather is not so fine, our payoffs would be lower, right? So nature somehow influence the game. Here, nature in this particular game, nature distributes chances. So for example, there is I think nature is the 0. It's a non-strategic player. So we present nature as the as a player in the game, but of course there are no payoffs associated with nature. So on Sunday morning, nature will decide whether we have a sunny weather. So let's say probability of 1/3 that it will be sunny. With probability 1/3 it would be a snow, and with probability 1/3 it will be a raining day. The worst probably, right? To go in the park. So nature decides from where we'll start, right? From this position. Well, here in this position, first player makes his move. In this position, a second player makes the first move, and here third makes the third move. It's like nature decides who will be the player who will make the first move. You can think about nature here as just throwing a coin, or how to call it in English. Then you decide who will be the first. You just take 3 matches and you break one of them to make it shorter, and then players, they just take their matches, and the one that is shorter will be, this player will start. So it's basically exactly what happens here. So nature distributes chances. So here it's just another example of the game with the nature. So here nature decides here. So 0, this is how we represent nature. So A make his move, and then there are 1/3 probability that now it's time for the second player to make his move. It's probably B. B is probably name of the player, and 2/3 probability for C to make his move. Or maybe it's the same player making different, with different possible menu of actions. So I hope this idea of nature is clear. So it's basically something outside of players. It's not necessary like nature in a direct meaning, like weather. It can be something different. Just pure chance decides what will happen next. You can think about card games as the game with incomplete information. For example, poker. In a poker, we have both imperfect information, because I'm not aware what cards my opponent has, right? So it's imperfect information. But also it's a game with incomplete information, because nature decides the chances. Okay, so I promised you that we'll introduce this term information set. So information set. Information set is a set of nodes that cannot be distinguished by a player. So this is how we show information sets on the tree. So this player, let me tell the story about this game. If you are into military history, maybe it is familiar to you. It's a story about Waterloo, Battle of Waterloo. N is Napoleon, and G is his general. I forget his name. Grouchy, something like this. I think I have it somewhere later in the slides. Grouchy. So the story about this game is that Napoleon sent Grouchy to find the troops of his opponents. I think they were Prussians. And then Grouchy, then he needed his help. He needed the help of Grouchy, and sent him a letter asking to go back to help him. So Napoleon sends a letter to Grouchy asking to go back to help to Napoleon. Grouchy has to decide whether to go back to Napoleon or to engage into fight. If he engaged into a fight, then he cannot help Napoleon. So and Napoleon have to decide whether to wait for Grouchy or fall back. What actually happened is that Grouchy get engaged into the fight. Napoleon asked for his help, but didn't get it. And then Napoleon said that the reason why he lost Waterloo is that Grouchy didn't came to help him. So it's basically send, fight, wait. I think this is what happened. So -10, -10. They fight for the theme, like Grouchy was the general of Napoleon, so that's why they negative outcomes for both of them, like the worst possible outcome. So basically, it happened as a dynamic game. So Napoleon sent a letter, then Grouchy decided whether to engage into fight or not, and then Napoleon decided whether to wait or fall back. But the problem is because there are no telephone, there is no quick way to communicate. They basically had to make their decisions. Basically, it's like a simultaneous game. So Grouchy had to decide whether to go back or fight before he get the message from Napoleon, and Napoleon had to decide whether to wait or fall back without information from Grouchy. Is it clear? Do you have some questions? Because it's really important for you to understand this idea of information set. So why they cannot distinguish? So is it clear from this story why they cannot distinguish?
Yes, it is clear.
Okay, thanks. So information set is a set of nodes that cannot be distinguished by a player, and trivial information set is a set which has only one node. So we are familiar with trivial information set since the last lecture, but we haven't called it this way. It's like, you know, this joke about one person who just find out in his late years that he was spoken prose all his life. So it's a similar case. So just if in the game with perfect information, like here, the game we've discussed, king, well, here we had information set, but now it is presented without information set. So let's say it's a game with perfect information. So king makes his decision, then his servants, are they merchants here? No, make his decision perfectly aware what king decided, and then peasants make their decision perfectly aware. So these nodes, all these nodes, they are trivial information sets. So they are trivial information sets with only one node. So if all information sets are trivial, we have a game with perfect information. So all of them are trivial. So we have a game with perfect information. So let's discuss. How we can analyze games with information sets. Well, when we were talking about this game of Napoleon and Grouchy, we had this idea that it's a basically static game, even though there is some like consequence of events, but because they don't aware about what their partner in the game did, it's basically like a static game. So that's why we can present this game as a static game. So there are two possible ways how we can present. I think at the very end of the last lecture, you had a question about it, and I promised that it'll become more clear later. So this is basically the story. So here we have rock, paper, scissors game. Of course, it's familiar to all of you, and it's a static game because the very point of it is that I don't know what you are going to show, because if I can see that you are showing me scissors, I should throw rock and I will win for sure. And you can think like you're saying you're playing it with a robot, and robot is very fast. And for robot it's a dynamic game, so robot is aware what you are going to show immediately, and it always wins, right? If it's a dynamic game with perfect information, at least for one player, well, then it's not perfect. But if for one player has perfect information, this player will always win, right? But if both players have imperfect information, then this is how we can present it as a dynamic game. So first player decides what to show: rock, paper, and scissors. Then second player make his move, but second player cannot distinguish between rock, paper, and scissors played by the first player. Let's say as humans, we are pretty slow, right? So even if my eyes kind of see what you're showing, my brain is not fast enough to give me what are you doing actually. So I have to, like with penalty kick, I have to make my decision, rock, paper, and scissors, without being able to distinguish between these three states: this one, and this one. So this is information set. So this is information set. And these are two ways how we can present. These are two ways how we can present game with imperfect information. So we can draw a tree with information sets, non-trivial, of course, information sets, or we can make a table. And when we was discussing static games, we learned how to find Nash equilibrium, right? So you can use best responses to find Nash equilibrium for this game. Well, to look for it. So let's discuss our assumptions about information sets. So what is possible for information sets and what is impossible? So first of all nodes in one information set must belong to one player. So this is impossible. I'm showing on my slides, I'm showing you what is impossible. So it's impossible that here we have player one and here we have player two, and these two nodes, they are in one information set. No, it's impossible. It's like, I don't know who I am. Maybe I'm myself and maybe I'm a student in this group, and based on this, without being aware of who I am, I need to decide what to do. So whether to listen to the lecture or whether to participate in this meeting or not, that would be funny. No, so we assume that this is impossible. So player is aware who he or she is. He just or she cannot distinguish between what previous player did. Right. So this is impossible. Second, number of moves at each node in an information set must be equal. So again, what we have here is impossible. So we have two nodes in the same information set. And here two actions are available, R and P. And here, 3 actions are available, R, W, and P. So this is impossible. In one information set, we have just two possible we should have the same number of actions that are available to them, probably 2 here. Moves at each nodes in information set must be identical. So here again we have something that is impossible. Here here in the first node E and F are available, but in this node G and H are available. It's impossible for one information set. It's impossible. What is possible, though, although it's kind of very strange, it's a weird situation. It's so-called games with imperfect memory. So look what happens in this game. So second player makes his decision, so it can be T1 or B1. If it's T1, then first player can decide between T1 and B1. If it's B1, then first player can decide between capital T and capital T2 and capital B2, right? Then it's second player. It's time for the second player to decide. And now first player decides. And what is funny and strange here is that first player cannot distinguish between these two branches, like up branches and low branches. But first player was able to distinguish between branches here. So it's like in these nodes, the first player forgets about what he was aware to him, the knowledge that he had here. That's strange. So that's why it's called imperfect memory. But it's possible. So these models are used to model like human behavior. For example, models with imperfect memory. Here you can find another example of a game with imperfect memory. So the first player decides between T and B. If first player has chosen B, then second player can choose between small t and small b. And if second player has chosen small b, then first player can choose between capital T and capital B. But what is strange is that first player cannot distinguish between these two nodes. It's again like here first player forgets about whether he made decision here or not. So it's possible, but it's strange. So usually we don't expect players to behave this way. So this is not what we usually expect from the game. So information sets and complexity of the strategy. Complexity of player strategy can be described as number of elements in the strategy. And number of elements is basically number of players' information sets. So a week ago, when we were discussing perfect information dynamic games, we were just counting nodes. Do remember I've shown you that, for example, if player has one node, then there are just one element in his strategy. For example, for this is a perfect information game, right? So here for king, his strategy has just one element, and this element can be high or low. as for M, it is a bit more complicated because there are two nodes, and that's why there are two elements. So possible strategies are collect, 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 not collect, not collect, collect, not collect, not collect, right? So strategy consists of two elements, two possible elements. As for peasants, their strategies, although this is kind of strange, like only rebel is possible, then it's not a decision, it's like automatic. So probably we should not count it as the part of strategy. So P is to make, you can just forget this action and just put terminal node here with payoffs. So it means that for peasants, there are three nodes, like three real nodes, and there are three elements. Oh, sorry, again, this can be ignored. So there are two real nodes. So, and there are two elements like rebel, 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 not rebel, not rebel, rebel, not rebel, not rebel. Now, if we apply the same idea, to imperfect information game, we count these two nodes that are parts of one information set. We count them as one element for the strategy. So look, a Napoleon strategy consists of two elements because Napoleon has two information sets, one trivial here and one non-trivial here. So trivial is that we have a perfect information. So here Napoleon has perfect information, but here Napoleon cannot distinguish between two states, this state when Groucho decided to go back, and this state when Groucho decided to fight, to engage into fight. And so this is one information set. So what are strategies available to Napoleon? They are send, wait, send, fallback, not send, wait, and not send, fallback. I hope it's clear. As for Grouchy, he has just one non-trivial information set. It means that his strategy has just one element, and this element can have two possible values. It's go back and fight, right? So just one element strategy. Any questions? Is everything clear?
Yeah.
Usually people don't have questions if everything is clear and nothing is clear. I hope it's the first case. So example of a game with information set, non-trivial information set. So it's a story about Beckham, so football player. Beckham needs to decide whether to approach Real Madrid or not. Approach, don't approach. Then Real makes his decision to seek opinion of advisor or don't seek opinion of advisor. So if he decides don't seek opinion of advisor, we go here, right? So advisor needs to decide without being distinguished these two information sets, these two states, sorry, these two states. The difference between them is that here Beckham approached Real Madrid, and here Beckham didn't approach Real Madrid, right? So advisor makes his decision to make a negative recommendation or positive recommendation, negative recommendation, positive recommendation. So if it's a negative recommendation, then Beckham can decide between Bayern and Milan. If it's a positive, Beckham still can decide, but now between three clubs: Real Madrid, Bayern, Milan. Is it clear? I mean, I think if you at least somehow interested into football or soccer, it's more familiar. So it's basically a story of football player, football club, and advisor. So it's story about enrollment. Should Real enroll Beckham? So both Beckham decides on the club, and Real Madrid is the best and the most wealthy club in the world at the moment, needs to decide whether to hire him or not. So let's count. Information sets and strategies. So how many strategies do they have? So what about Beckham? How many information sets Beckham has? What do you think? So how many information sets does Beckham have?
I guess 3.
Why 3? So look, the first here, second here.
It's like
here.
okay, understood. The different, because I think it's like about not information set, but it's about nodes, or information set is the way he can. I don't really understand the difference. Can you repeat, please? Because I thought that like Beckham for real, Milan and the last one, and these two are like one information set.
Great. Look, it's somewhat similar to mixed strategy Nash equilibrium. Then we learned that pure strategy Nash equilibrium is also mixed strategy Nash equilibrium, but a special case of it. So the same, you can think about the nodes without like this new element for us. So it's just simple nodes, but it's still information set. It's just called trivial. So look here. So trivial information set is a set which has only one node. So here we have a trivial information set. Here we have a trivial information set, and here we have a trivial information set. So these 3 nodes, they are trivial information sets. But these 4 nodes, they form 2 information sets. So they are non-trivial. One non-trivial information set, another non-trivial information set. So the right answer, if I ask you how many information sets does Beckham have, you should say 5, 3 of them trivial and 2 of them non-trivial. So this is a full answer. So what about Real Madrid? Can you count information sets? So how many information sets does Real Madrid have?
2, and all of them are trivial.
Right. And what about advisor?
1.
Mm-hmm.
The
non-trivial. Right. So the first task is done. So we counted information sets. So what about strategies now? Let's start from advisor. So how many strategies does advisor have?
May I ask a question about information sets?
Yes.
Why do we unite into these 2 different information sets? I mean, for example, for Beckman, the case when he can choose between Bayern and Milan in case of Real, if in case of negative recommendation, and when he can choose between Bayer and Milan in case of not seeking opinion of the advisor.
No, it's just this picture is not immediately clear. Look, if Real decides don't seek opinions, we go here. Can you see it?
Yes.
So here, advisor cannot distinguish between situations then Beckham approached Real and Beckham don't approach. So between these two things, these two states, advisor can distinguish. But if Real decides don't seek opinion, then it's time for Beckham to decide between Bayern and Milan. So basically, here Real decides, well, we don't need.
And yeah, and if we talk about Beckham, why we say that there are only 2 information sets but not 4?
Wait, you're talking about Beckham. So let's count. We have one here, right? We have second here. We have third here. So 3 nodes with perfect information. So they are trivial information sets. Nodes with perfect information, it's a case of trivial information sets. So Beckham cannot distinguish between states here. But we have also 2 non-trivial information set, one here and one here. So what happens with Beckham is that Beckham doesn't have information whether Real asked advisor or didn't ask him. So maybe for Beckham, it's like maybe Real just immediately decided that they don't need me and that's why they haven't consulted anybody. Or they thought that maybe they need me, but they ask advisor and advisor advised against it.
Okay, so, thank you, I got it.
It's sometimes it's similar what happens in real life. Then you participate in some of competition. I don't know, for example, you try to find a new job or you submit a paper in a journal or I don't know, you participate in some competition, then some jury decides on you and you don't know what happens there. So maybe you was very close to winning, but you just don't know about it. Or maybe from the very beginning, they decided that they don't need you. You just don't have information about it. So what we wanted to do, we wanted to count strategies. So let's start from advisor. It should be easy. So how many strategies are available to advisor? So
negative recommendation and positive recommendation.
Right. So advisor has only one information set. It means that his strategies have only one element in them. So his strategies consist of just one element. And this element can have 2 values, just 2 values, 2 actions available, negative recommendation and positive recommendation. So you're perfectly right with your answer. So what about Real? So how many elements Real's strategy has? So what do you think? How many elements does its strategy have? Again,
I guess 2 because it can seek option or don't seek option opinion in both information sets.
No, wait. Yes. First of all, how many elements? You said 2, but then you kind of contradicted yourself. 2 elements because we have 2 nodes, this node and this node. And for every element, 2 values are possible, seek opinion and don't seek opinion. So basically, if we count strategies, there are 4 strategies. The first strategy is to seek opinion if Beckham approach Real. So basically, Beckham asked them, would you like to enroll me? Would you like to hire me as a footballer? So Real has this information from Beckham, right? So, for example, they can decide if he is interested in playing in Real Madrid, then we'll seek opinion about him from advisor. But if he is not interested, then we'll don't seek opinion. So their strategy, seek opinion, don't seek opinion, right? Or their strategy can be, in both cases, ask advisor about his or her opinion. So then their strategy is seek opinion and seek opinion. Or, so we discussed two strategies. There are two more. So one of them is, in both cases, don't seek opinion. And finally, but kind of strange, is to don't seek opinions, to not seek opinion if Beckham is interested in playing in Real Madrid, but seek opinion if he is not interested. That's a bit strange from like common sense, but still possible. So because Real Madrid has two information sets, there are two elements in his strategy, and every element, each element has two possible values: seek opinion, don't seek opinion. So that's why example of strategy for Real Madrid is first element, seek opinion, second element, don't seek opinion, for example. Now, what about the most complicated case? So what about Beckham? So how many elements does his strategy have?
14.
40?
14.
14? Why?
Because he can, like, if approach Real Madrid, and after that to have Real approach Real, and where approach and Milan and Milan, if advisor have positive recommendation, and Real seek his opinion.
Look, there are 5 information sets for Beckham, right? This one, this one, this one, this one, this one. That's why his strategy consists of 5 elements. 5, the same as number of information sets. 1, 2, 3, 4, 5. Like this. Oh, sorry. What happened? Here's an example. At his node, he can decide to approach. So then it's approach. At the second node, here he can decide, he can choose Real. At third node here, he can choose buyer, for example. Buyer. At this node, he cannot distinguish, but he can choose buyer, for example. And finally, in this node, he can choose, let's say, buyer again. So this is an example. This is an example. But of course, for every node, other values are possible. So here it can be don't approach. Here it can be Milan, for example. Is it clear what I'm doing here? How I'm counting them? Is it clear? Okay, seems like our time is over. We'll continue from the same moments, from the same slides next time. If it's not clear, just prepare your questions for the seminar and we can discuss it. So if you don't have questions, you can just leave. If you have some questions, I can answer them. So I'm here. Questions? Bye. No questions? Okay, no questions. Thank you for the class and goodbye. Have a good holiday tomorrow. Bye.